Today we began our discussion of palladium catalyzed reactions, and we got to it at the end of class, and I know it was a little rushed, so I wanted to spend a little bit of time going over some of the details so that it'll be a little easier for you to work on the daily problems that you'll be working on for Friday. So what I want to do is go through the reactions that you're going to study, look at mechanistic steps, and then go through the catalytic cycle. And obviously we'll talk more about this stuff on Friday, but hopefully this will give you enough information to feel a little bit more comfortable when you work on the problems. So the Heck reaction is what you're doing in lab. I don't want to go through any of the details of that reaction. If you want more details on that, the mechanistic cycle, the catalytic cycle for the mechanism is on the Moodle page for the labs. So just check that out, you'll see it there. If you haven't talked about the mechanistic details yet in lab, you'll do that shortly. The Stille reaction is what we talked about today. So this is the reaction from lecture, again, where we have some sort of carbon tin reagent reacting with some sort of carbon halogen reagent, catalytic palladium, and we form a carbon-carbon bond. The Suzuki reaction. The Suzuki reaction is just like the Stille reaction, except we're going to use a different metal. So we can take the exact same substrate, and instead of using tin, we're going to use boron. Right? So we'll use something that looks like this, which is called a boronic acid, but we're going to use a carbon-boron bond, and that will eventually become the carbon-carbon bond that we want. So again, boron in place of tin. When we do these reactions, again, it's going to be catalytic palladium 0. The only difference is for a Suzuki reaction, we have to use a base. Without a base, the reaction will not occur. And again, we'll make the exact same product that we did for the Stille reaction, right? Again, just using a different metal. And we'll talk in class why you would choose one of these over the other, right? For right now, the key is to know that it's going to look exactly the same. And then the other reaction is the Sona Gashira, which is also quite similar, but it enables us to form a bond to an alkyne. Right, and for the reaction conditions for the Sona Gashira, it is a little bit different in that you have to have catalytic palladium and catalytic copper. The mechanism is a pretty interesting one in which you're able to make a bond between the alkyne and the copper. And so essentially you've got carbon copper here, carbon boron, carbon tin. Those are the different metals that we're going to study. And to get this reaction to work so that you can make that carbon copper bond, you have to have some sort of trialkylamine, and that will produce that product, which again, there's no other way that we can make that compound. All right, so some really interesting reactions. And the key thing here is that for these reactions, they all have the exact same mechanistic steps. So when we think about the mechanism for these reactions, they all start with first an oxidative addition. All right, we talked about that today, and the oxidative addition is just like what happens when you add magnesium to an alkyl halide and you form a Grignard reagent. Right? So when we do an oxidative addition, it's going to be some sort of alkyl halide. Actually, alkyl is probably the wrong term. Right? We want to make sure that we're clear on this, that it's going to be some sort of vinyl or aryl halide. Right? Again, not alkyl. We're not going to make bonds to sp3 hybridized carbons. Right? So a vinyl or aryl halide plus palladium 0. Right? That's what we're going to start with. Right? And so the reaction is like we talked about in class today, right? So that if you have, for example, a vinyl iodide, react that with palladium, right, what we're imagining is the palladium going to insert between the carbon iodine bond, right? So we can imagine that we're going to form a bond between carbon and palladium, and then between I and palladium, right? And since it's palladium 0, palladium has lots of electrons, so you could imagine drawing curved arrows that look something like that. Organometallic chemists rarely draw curved arrows because the processes are never really this simple, but I think it might help us think about and understand what might be going on, right? So that would end up generating something that looks like that. And again, now this is going to be palladium 2, palladium plus 2, like we talked about in class, so that we have oxidized palladium from palladium 0 to palladium plus 2, right, which is an important point. Okay? So that's oxidative addition. The next step is going to be transmetallation. Right, and the key point about transmetallation is that's the only difference between these three reactions. Right, so this is the only difference. Right, and the difference is we have tin, boron, or copper. Right, so tin, boron, or copper. And there are many other metals that participate in transmetallation. It's just these are the three that we're going to talk about because they're the most common. Right? And what happens in transmetallation is that we're going to create a new carbon-palladium bond, and we're going to do that taking advantage of some sort of carbon-other metal bond. Right? So this will enable us to generate a new carbon-palladium bond and remove the palladium halogen bond. Okay, so what will that look like? All right, so one example of this would be if we had the same compound over there. So if we had, I'm just going to change how I'm drawing this to make it a little bit easier. So we'll just flip it over. And if we reacted that with a boron compound, and we'll see when we talk in more detail about the Suzuki reaction that it has to be a borate, it has to be a boron that has a negative charge, right? So this would be the Suzuki reaction. Right, if those two things come together, right, we're going to form a bond between I and boron, and then a bond between carbon and palladium. Right, and we can draw the curved arrows such in some way like this, where we have, in this case, the phenyl group and the iodine just switching spots, right, and then that will give us our new palladium species. And again, this was palladium 2. This is still palladium 2. And then the iodine is now on the boron. All right. So again, we've kept the palladium, still palladium 2. We've just swapped a carbon group from boron onto palladium. Right. And the next thing that we'll do is we'll do the final step, reductive elimination. All right. In reductive elimination, we're going to form the carbon-carbon bond that we need in the compound, and we're going to regenerate the catalyst. Right, so this is formation of the carbon-carbon bond and regeneration of the palladium 0 catalyst. Right? And so if we were looking at the Sona Gashira reaction, we would have something that looks like this. Palladium 2. Right, so we could form this in a Sona Gashira reaction, and then in the reductive elimination step, we're going to form a bond between those two carbons. Right, so we could imagine electrons flowing to make that bond, and then electrons from that bond going on to palladium. So palladium is being reduced, so we're going to generate the carbon-carbon bond that we want, plus our palladium 0 catalyst that we're going to use to do another cycle in the catalytic cycle. Right? So again, in this reaction, we've taken palladium 2, it's gained 2 electrons, and it's been reduced to palladium 0, and we formed the carbon-carbon bond that we want. Right? So let's just finish up by going through the mechanism. Right? And I'll write it out similar to the way I wrote it out in class today. So if we start with our palladium 0 catalyst, and we'll use bromobenzene like we did in class today. We do the oxidative addition step. We generate our palladium 2 intermediate. The next step is going to be transmetallation. And I'm just going to write this as a generic transmetallation, where we're going to take some sort of R group attached to a metal. As we've talked about, we're going to use either copper, boron, or tin. And then over here, we're going to have bromine attached to the metal. Right? And again, we'll talk about the specifics that are happening here. But just to be clear, M equal the tributyl tin is stili. M equal to boron, and I'm going to say plus hydroxide, is Suzuki. And M equal to copper is Sona Gashira, right? And so this will replace bromine with the R group. Still palladium 2. And then we'll do our final reductive elimination step. Which will generate our product and regenerate the catalyst. So the key thing is that this catalytic cycle is the catalytic cycle we're going to use for Suzuki, Stili, and Sona Gashira reactions. The only difference is in the transmetallation step. Right? So hopefully this helps you think about what's going on in those reactions as you work on them on the daily problems. And also think about how this mechanism, the first and the last steps, are the same for the Heck reaction. It's just that there is no transmetallation in the Heck reaction. We have other steps in there, and we'll talk about that on Friday as well.